Recall that for a combinatorial structure, you've got building blocks, something well defined, and you have rules for putting them together. Also has to be carefully defined. So far, most of the things that we've been using for building blocks are sets, elements in a set. Sometimes, though, you need identical building blocks, indistinguishable, as opposed to when we say they're different or distinct elements. And the correct format for that is multisets. So let me show you what a multiset looks like. X is a multiset here, and it has A, B, B, G, F, 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 and G. So it has multiple copies, hence the name. Those are identical B's and identical F's and identical G's. The second line shows another way of writing the same multiset. You can list the different elements, the distinct types of element, but instead of writing them multiple times, you can put out front how many there are. So 1A, 2 B's, 2 G's, 3 F's. Here's another one that we'll use in a minute. It has all those letters, which you can see spell something. And there's the other way of writing it with 4 times I, 4 times S, 2 times P. Now, so the first thing we'll build using a multiset are the combinatorial structure called multi-combinations or multi-subsets of, usually listed, a size K. Alright, well, here's what some of those look like. We'll start with the set X and get all the size 3 multi-subsets, or sometimes they're called 3 multiple combinations of X. So here they all are. First of all, there were 3 elements that looked different, A, B, and G, and F. There were 4 different kinds. So that means we've got those on the left, the 3 multi-subsets that have 1 of each. But then we also have all these multi-subsets that have both of the B's, down at the bottom, both of the G's, and then in the middle there's some with 2 F's and 1 with 3 F's. That's all you can make using subsets of those letters. The rule is, of course, that you can't use a letter more times than it is in the original. They all have to be multi-subsets. It looks like there's 14 total of those. So we'll keep that in mind because the goal we have is to count these without listing them. Just like we can count subsets of a set, we want to count multi-subsets of a multi-set. So leave some space there, and here's step 1 in the goal. I think we can do step 1 here. Step 1 is to look for 3 multi-combinations of a new multiset. Z is equal to infinity A's, infinity B's, infinity G's, and infinity F's. In other words, it's an infinite size multiset, and it has an infinity of each of those 4 types in it. So if we want 3 multi-combinations there, we're allowed to basically have as many of anything as we want. Up to 3, of course, because it's a size 3 multi-combination. We have 3 A's, and we still have all the old ones. We have A, B, and G. So the idea is to count all of them and subtract off the ones that we couldn't make with our set X. Well, so first though, we just want to count the 3 multi-combinations of Z, and that requires an interesting idea. The 4 types of elements, A, B, G, and F here, are like 4 shelves from previous problems, and what we have are 3 blanks to fill in our size 3 subset. Think of them as 3 blank elements that we need to assign to one of the 4 types, or to put on one of the 4 shelves. In fact, you can draw a picture of 4 shelves down here and just give them names, shelf A, B, G, and F. And then picking 1 A and 2 G's is exactly like planning a bookcase with 1 in the A and 2 in the G shelf. And so what that really is a bijection between plans for bookcases and multi-subsets, where the number of shelves is the number of types and the number of locations to plan for is the size of the multi-subset. And that's the bijection shown right there. That picture corresponds to AGG. So it's the same way to count them. The number of 3 multi-combinations of that set Z is just 3 plus 4 minus 1, choose 4 minus 1. Comes out to 6, choose 3, which is 20. And here's one thing on the side I should mention is Pascal's triangle. We're going to talk about it a lot in chapter 5, but for now I'll mention how it's helpful if you have to do a quick calculation. You start at the top with a 1 and then 2 1s underneath it and you skip a space. Then 1 2 1, 1 3 3 1. The way I'm getting those is by adding together the 2 numbers above every number in a row. So 1 plus 2 is 3 and 2 plus 1 is 3. It always starts and ends with a 1. And then if I want to find 6, choose 3, for instance, the secret is that the rows of Pascal's triangle there tell me the combinations. So 6, choose 3 is the 6th row, and it's the one that starts with a 1, and then the next number is a 6. And then you go over counting starting with 0, 0, 1, 2, 3, and that 20 there is the answer to 6, choose 3. Or you can use the formula with factorials. That works just as well. That's how I got the 20. And then at the very last line, I wanted to show some new notation. This isn't even in our book, but if you look up multi-combinations on Wikipedia, they'll show this notation. It's the double parenthesed combination. And 4 choose 3, 4 multi-choose 3 is how you would say it in the double parentheses. That's equal to 3 plus 4 minus 1, choose 4 minus 1. In other words, in general, k multi-choose n is equal to k plus n minus 1, choose n minus 1. All right, step 2 coming up.